This is a presentation of our tool desync-cc, an automatic disassembly-desynchronization obfuscator. My name is Ulf Kargén, and this is work done together with Ivar Härnqvist, Johannes Wilson, Gustav Eriksson, Evelina Holmgren, and Noel Trameri, all of us from Linköping University, Sweden. So the general aim of code obfuscation is to delay or prevent reverse engineering of binary code, which is an important topic both from the defensive point of view when trying to prevent intellectual property theft, but also very much from the offensive point of view when, as a malware analyst, for example, you are faced with circumventing the obfuscation in obfuscated malware. So the first step of reverse engineering a binary is to translate the machine code into assembly mnemonics using a disassembler. And based on this, you can then either manually reverse engineer the code or use a decompiler to retrieve a high-level representation of the program logic. And most existing code obfuscators apply various types of control flow obfuscation to try to prevent these two activities. And there are many different types of techniques that are described in the literature, and also a number of different tools, both free tools and commercial tools for doing this. Two notable examples of free tools are the Tigris source code level obfuscator and the intermediate representation level obfuscator LLVM. Now, in our work, we focus on the complementary approach of disassembly-desynchronization, which targets instead the first step of the reverse engineering process, the accurate translation of machine code into assembly code. And while this is a technique that's quite frequently encountered in malware, it has received comparably less attention in the literature, and also, to the best of our knowledge, there are no publicly available tools to apply this type of obfuscation. The technique is applicable on CPU architectures with variable length instructions like Intel's x86, where you can trick the disassembler to parse the instruction stream at an incorrect offset, thereby desynchronizing the disassembly and hiding a number of actual instructions in the code. So benefits of this technique include first being orthogonal to control flow obfuscation techniques. So you can apply both as an added layer of defense against reverse engineering. And also it offers a much greater degree of granularity than a source code or intermediate representation level obfuscator. So you can hide individual instructions like specific function calls and so on. Typically, the technique is implemented by inserting junk data into a binary protected by a fake branch that will always jump past this junk data during runtime. So if we wanted to, for example, hide the call to this secret function here, we would first insert a piece of junk data, in this case 1 byte with the value EB hexadecimal, just prior to the instruction or instructions we wanted to hide. And then we would insert a so-called opaque predicate, a statically invariant condition. So here we simply set the EAX register to 0 using XOR and then test if EAX is 0, which will of course always be true. So when we branch on that condition, we make sure to always jump past the junk data during the runtime so that the behavior, the semantics of the program remains unchanged. And if we run this through a x86 assembler, we get the following machine code with the call instruction underlined here. If, however, we were to run this through a disassembler, the disassembler would assume that also the fall-through branch is valid, even though it can never actually be realized during runtime. And if the disassembler would parse the code down that path first, we actually get a completely different instruction listing. And the reason is that the junk byte EB together with the first byte of the call instruction E8 actually decodes to a valid jump instruction. So the disassembler would consume the first byte of the call instruction, thereby desynchronizing the instruction stream. And then the disassembler would have no choice but trying to decode whatever is left of the call instruction. So here we see that the second and third byte actually happen to decode to a valid branch instruction, and also that the two last bytes decode to a valid XOR instruction. So we see that the same machine code can actually be disassembled into two different instruction listings depending on which path the disassembler follows first. And that is this phenomenon that we exploit for implementing disassembly desynchronization. Now, in addition to inserting junk data that is protected by an always taken fake branch, we can also insert a never taken fake branch into the middle of an existing instruction to achieve the same result. Now, with the background out of the way, we can begin discussing the actual design of our tool. So the motivation for creating the tool was first to provide a testbed for experimenting with disassembly desynchronization, for example, to evaluate how resilient existing disassemblers are to this technique, but also to allow future research. We could, for example, use the tool for ground truth generation to produce large amounts of obfuscated code for training a machine learning based obfuscation detector, or to evaluate new detection or deobfuscation techniques. And to support these use cases, we designed desync-cc as a drop-in replacement for GCC, where you essentially simply set the cc variable and run your makefile as usual, and then the obfuscation is applied automatically during compilation. We also designed the tool to be highly configurable, so you can use, for example, a regular expression to control where to insert the desynchronization points. You can select different types of epoch predicates and so on. And also we support both this never taken and always taken type of fake branches to further increase the confusion for reverse engineers. From a technical point of view, we designed desync-cc as a wrapper around GCC, where we intercept the intermediate assembly files after code generation and perform control flow graph reconstruction and register liveness analysis, so that we can safely insert these epoch predicates without interfering with the program semantics. We cannot, however, make the final selection for the values of the junk data at this point, because that will depend on the layout of the executable. So instead we insert placeholders for the junk data and emit symbols for each desynchronization point, so that after assembly and linking, where we have an executable, we can iterate over the symbols in the binary and do a essentially brute force search to find desynchronization inducing junk bytes. And this is actually quite fast, so we require on average around 2 trials per desynchronization point on average. And this is also the point where we find the offsets for this never taken type desynchronizing branches. And by patching up the intermediate binary in this way, we produce the final obfuscated binary. So to give you an idea about the performance of our tool, we also performed some preliminary evaluation. So to test the performance during building, we inserted desynchronization points every 5 instructions into the GNU core util programs. And here we observed around a 4 times slowdown in the build process. We had a success rate of actually 100% in finding desynchronizing junk bytes, a little bit less for the never taken type of branches. The performance during runtime, when running the obfuscated code, depends heavily on the type of epoch predicates used and the desynchronization insertion frequency. But as an example, we inserted desynchronization points before every call instruction in 2 different programs, essentially hiding every function call. And this resulted in slowdowns of 13% and 0% respectively. And it turned out to be a quite cost-effective use of the obfuscation, because this prevents call graph reconstruction, and so this is used as part of the disassembly process by, for example, the state-of-the-art disassembler IDA. So we can actually essentially completely prevent code recovery by hiding every call instruction. So in conclusion, we presented desync-cc, a tool for automatic application of disassembly desynchronization during compilation, in the hope to further future research into new obfuscation techniques and countermeasures. It's designed as a highly configurable drop-in replacement for GCC using a 2-stage obfuscation process. And the code is available on GitHub at the following URL. And with that, I conclude my presentation. thank you very much for listening.